Hey guys, what's up? My name is Gabe and this is Games with Gabe, and this is the next episode in the Coding a 2D Physics Engine in Java series. This episode is super cool. So, by the end of this episode, we will have a physics system that is able to apply linear impulse to circles. So you see I got the red circle falling, and he's the only one affected by gravity, and you can see that the linear impulse affects all the objects just as you would expect it to. And the collisions get resolved and everything. So, very exciting. This is also pretty difficult to understand the concepts, so we're going to talk about the concepts before we actually start coding, but this is what we are going to get to. So, let's dive right into this. Alright guys, I will try to explain the physics to the best of my ability, but this is definitely not my strong suit. So, there is a research paper linked in the description that explains this way better than the explanation I am most likely going to give, but I'll give it a shot. Okay. So, say we have the two circles that are colliding and we want to figure out how to apply the correct impulse to resolve the collision. And the reason we're applying an impulse to resolve the collision is because that's basically how real life works. So if two objects collide, what ends up happening is they get some velocity applied, which is called an impulse. That's basically like an instantaneous change in velocity is the appropriate term. So you have a change in velocity that is instantaneous, and in real life, it's not actually instantaneous. It happens over a small amount of time. But for our purposes, we consider it to be instantaneous. And what happens is basically if you have like this object colliding with this one, what will end up happening if his velocity is pointing this way and his velocity is pointing this way is this circle will most likely go a little bit more like this. And this circle will probably go more like this since this one supposedly has a bigger mass than this one. Okay, and that's all an impulse is. It's figuring out how do we figure out how to change the velocity right now while they're colliding so that it goes to this way. And then once we have changed those velocities, they will no longer be colliding. And so that's how we have resolved our collision. Well, we can use the laws of physics to figure this all out. So in order to do this, what we're going to need is the relative velocity between the two objects. So this is velocity of B, velocity of A. The relative velocity would be the velocity of B minus the velocity of A, which would give us some relative velocity. Just basically something shared between them. How fast are they going in respect to each other? And then what we need is actually the magnitude of the velocity in the direction of the normal. Okay, and so the normal is just basically what direction they're colliding in. And what we want is how fast are they going with respect to each other in this direction. Okay. And we can do that since the normal is a unit vector. We can literally just dot the relative velocity vector with the collision normal, and that will give us the speed at which they are hitting each other in the direction of the normal. So this is like the speed of how fast they are hitting each other in the direction of the normal. Okay. Next, we need this other variable called E, which is the coefficient of restitution. And so all that is it's a fancy way to say how bouncy are they. If his coefficient of restitution is 1 and his is 0.8, what this means is he will perfectly bounce off any object he hits, whereas he will bounce off almost perfectly, but about 20% reduction in his speed. So it's almost like if you have a flat basketball and you bounce that on the ground, then it won't bounce as high as if you have it full. And so this would be like a full basketball, this would be like a flat basketball because the coefficient of restitution is lower. So just bounciness is what the E variable represents. And then we need our impulse. And so the way the impulse is defined is actually mass times the force, but you can derive that down to basically the impulse is the mass times the velocity, simplified for our purposes. And so this is what we're solving for basically is what is the impulse so that we can apply the impulse in the direction of the normal for this object and this object, which will then get us the appropriate velocity vector so that he's now going more like this and he's going probably more like this, which means then they'll be separating, right? And then we won't have to worry about the collision because it will have been solved. Okay, so in order to do that, we need to use conservation of momentum, which basically just says that the velocity of an object after a collision is the same as the velocity of the object before the collision, scaled by the coefficient of restitution. So the magnitudes too, not like the actual velocity, so like their speed. And so basically what we can say is v prime, the speed after will be equal to the speed before times the coefficient of restitution. And we do negative because the speed will be flipped because the collision will have changed the velocity in the opposite direction. Okay, now let's do a couple things here. So what we can say is if J is equal to the mass times the velocity, if the impulse is the mass times the velocity, well, then we can say the velocity is equal to the impulse over the mass, right? If we just move this over, then that's what we get. Okay, so basically what we can say is the velocity due to impulse is the impulse divided by the mass of whatever object you're dealing with. So what we can say is the velocity of an object after a collision is equal to, which we can rewrite as almost like the initial velocity plus this guy, the impulse, and we want to apply the impulse in the direction of the collision normal. So this is basically saying, okay, so if we want to find out what the true velocity would be after the collision, what we can do is we can add whatever velocity we currently have plus the impulse applied in the direction of the collision normal. So if we add the impulse applied in the direction of the collision normal, then what we will end up with is the appropriate final velocity, which is also equal to the negative coefficient restitution. The magnitude of this will be equal to this. And so this is sort of our conservation of momentum in action. And then this is us saying, okay, this is how we're going to get to our new velocity, but we have to make sure that this remains true. And so in order to make sure that this remains true, we just need to solve for an impulse that makes sure that that remains true. Because we know what the velocity before was, we know what the mass of the object is, we know what the collision normal is. Those won't change. The only thing that can change is the impulse. And so we want to make sure that the impulse ensures that this remains true, that we have maintained conservation of momentum. And so the way we can do that is basically, let's first of all say, okay, we know that the velocity in terms of impulse, the speed, so this isn't actually velocity, but the speed of the object with regards to impulse will be equal to negative 1 plus e times the velocity in the direction, the speed in the direction of the collision normal. So vr dot n, which I'm just going to expand that right here anyways. So times vr dot n. And the reason we add 1 here, so we said it was just negative e times the magnitude of v. Well, we know that magnitude of Vn is Vr dot n, so that's just magnitude of V. We're adding 1 to the coefficient restitution because we have 2 objects involved in this collision. So we have to add 1 to ensure that we're accounting for that. And then once again, it's negative because we have negative E. So this is the speed, this is not a velocity, but this is the speed with regards to the impulse. So this is how fast the impulse vector will be. So now that we have the speed in the direction of the impulse, we need to apply this speed in the direction that the impulse should be applied to each of these objects. And so we'll calculate the final impulse, which I'll call capital J, and that is equal to this lowercase vj, so the speed with regard to the impulse, how fast it's going, times the inverse masses of the objects, the sum of the inverse masses. And the way this was explained in the paper is basically we need to divide it by the inverse masses to make sure that we are applying the impulse evenly spread across both these objects. So since we have 2 objects and we want to imply impulse to him and we want to imply impulse to him, we need to make sure that we divide by the sum of the masses to make sure we get an even amount of impulse applied to each object. So this is our final impulse value that we can use to apply. And the way we apply it, remember, is we say v prime equals v plus j over m times n. And so now we can just use this capital J. We've solved. So we've basically done the resolution, and now we can just say, okay, so v prime of a is equal to va plus, and then we'll do capital J, since that's our impulse value spread evenly, times the inverse mass of a, which is just the same as j over m, right, times the collision. And then we can say v prime of b equals the original velocity of b minus the impulse times the inverse mass of b times n. And we do minus here because since va in regards to our collision is this object here, that's our point of reference, he would go off in the opposite direction as b. And so we just have to make sure that we do a plus and minus to make sure that they are different. And I'll show you what happens when you don't do that because it looks really funny. But anyways, I've done probably a horrible job explaining how all this works, but it's a very difficult subject, and I'm not a physicist, I'm a programmer, so I only understand this to my limited ability. Now, let's go and just plug in these equations to our code to see how all this will actually work once we get our physics system up. So let's go code this. All right, guys, so I am inside of our physics system 2D class, which is where most of the code we're going to be writing today is going to go. So the first thing we're going to need to do is I'm going to just reorganize these variables a little bit so that it's a little easier to see which variables are grouped together. Now, we're going to need a couple new variables too. And this is going to be two more lists of rigid bodies, and we're going to call this bodies 1 and bodies 2. And these are going to be the currently colliding rigid bodies. And then we are also going to need a list of collision manifolds, and these are going to be the collisions that are currently happening in whichever frame that we are on. So basically this will hold the bodies, and it'll basically be like a concurrent list where we'll have some body here, here, and here in list 1, and then one here, here, and here. And this guy is colliding with this is colliding with this, and so on and so forth. That's how this is going to be set up. Now, let's go down here, rearrange the variables to match over here as well. And I'm just going to say this dot bodies 1 equals a new array list. This dot bodies 2 equals a new array list. And this dot collisions equals a new array list. All right, so now we have all of that set up, we can actually start doing the code. So inside of our fixed update method right now, what we have happening is we update the forces, and then we update all of the velocities of the rigid bodies, which is good, but we're gonna have to add one more step into there, which is, well, two more steps. Find any collisions, which is currently only circle versus circle, and then we're going to need to resolve collisions via impulse resolution. And so this is where we're going to be resolving those. And so this is the order the steps will go. First, we'll find the collisions in the update. Then we will resolve them. And then we'll update the forces. No, I'm sorry. We'll find the collisions. Then we will update the forces. Then we will resolve the collisions via impulse resolution. Then we will update the velocities. And technically, you could update the forces before you find the collisions. That's fine. You just have to make sure that you update the forces before you start resolving the collisions, because then you could get some weird stuff if you don't. All right. So before we can do any of this, what we have to do is we have to say bodies1.clear, bodies2.clear, and collisions.clear. And we're basically going to set up a clean slate and say, okay, every frame we are starting off with no collisions and nothing is happening, which you could cache results and stuff. If two objects were colliding in the previous frame, they will most likely still be colliding in the next frame. So that's optimizations you can make down the road, but right now this is fine for our purposes. Next, what we're going to say is int size equals rigidbodies.size. Remember, rigid bodies is all of the rigid bodies that were added to our physics system, this list up here. And we will just go ahead and say for integer I equals 0 until I is less than size, I plus plus. Then for int j equals 0 and j is less than size, or actually, we'll optimize this a little bit. We'll say int j equals I until j is less than size, j plus plus. And what we're doing here is we're just iterating. This is the worst way to find collisions, but it'll work fine for us for now. We'll eventually upgrade this to be a quad tree or something, some sort of spatial partitioning scheme. But we're just going to loop through every single object twice and then check and see if the two objects are colliding. And then we'll say if I equals j, continue, because this means we're about to check the same object to see if it's colliding with itself, which will always be true, and we don't want to do that. We only want to do different objects. Then we'll say collision manifold result equals a new collision manifold. So this is basically saying, hey, if there are two collisions, we're eventually going to put the manifold in this result. Then we'll say rigid body 2D. R1 equals rigid bodies.get I, and then we'll say rigid body 2D. R2 equals rigid bodies.get J. So we get the first rigid body and the second rigid body. Then we're going to say collider 2D. C1 equals R1.get collider, which we don't have yet, but we'll have soon. Collider 2D C2 equals R2.get collider. And then we will say if C1 does not equal null and C2 does not equal null. So if they actually do have colliders attached to the rigid bodies, and if R1 does not have infinite mass and R2 does not have infinite mass, then we can continue on. So basically what we're saying is if they both have a collider attached to them and neither of them has an infinite mass, then we can check and see if they're colliding. Let's do the infinite mass real quick, and we'll probably do the collider too, just to get those in there. So we'll go into rigid body real quick, and then we'll say public boolean has infinite mass, and this will just return this dot mass equals 0.0, which was our flag to say this is an infinite mass object. This means the object will not move. It will just bounce objects off of itself, basically. Then we'll go ahead and create a set collider and get collider method. So we'll just say public void set collider, and then this will take in a collider2D, collider. We'll just say this dot collider equals collider, which we don't have as well, but we'll have that in a second. And then we'll just say public collider2D get collider, return this dot collider. And let's go up to the top and create a private collider2D collider. All right, now all is well again, and we can go back to physics system, and we have no errors if we spell things right. So if they don't have an infinite mass and they both have a collider, at least one of them does not have an infinite mass and they both have a collider, then we can go ahead and find the collision manifold. So we'll say result equals collisions dot find collision features, and then we will just pass in C1 and C2, which are colliders. Now we need to go into our collisions class, because right now we just have this find collision features, which takes in two circles but nothing else. So we'll say public static collision manifold find collision features, which basically just takes in two colliders. And this is nice to have because most of the time you're dealing with generic colliders, and we don't want to care about what the colliders are until we're inside here. So we'll just do this, and we'll say if C1 instance of circle and C2 instance of circle. So if they're both a circle, then we can just return find collision features C1, C2, which should be fine. And then we'll say else assert false unknown collider, and then we'll put C1.getClass plus versus, and then we'll say plus C2.getClass, which will basically just let us know, hey, we have not set up a collision response for these two colliders. And then we'll just return null. And this is giving us an error because if we go into our primitives and look at circle, it does not extend from collider2D right now. So we'll just say this extends collider2D, which it should because it is a collider. Then if we go back into collisions, this goes away. We're all good. If we go back into physics system 2D now, we are good here as well. So now we have the result. The result just goes and finds the collision features between these two objects, which would be any collider, but right now we know it's only going to work for circles, so if it's something else, it's not going to work. And then we can just say if result does not equal null, which means this succeeded, and we are not using this result. And result.is colliding, which we also do not have right now. So let's go into the collision manifold, and then we will just say public boolean is colliding, return this dot is colliding. All right, go back into physics system 2D. So if the result was not null and the result was colliding, then we know we have a colliding object. We want to add this to our collision objects because we do have a collision right now. So say bodies1 dot add, and then we'll say R1, so rigid body 1, bodies2 dot add R2, so rigid body 2, and then collisions dot add result. So we're basically just adding this to our list of collisions that are happening this frame, and that will be perfectly fine. And we don't have to worry about adding in the same collision twice because of the way we're looping. We're saying I until I is less than size and j equals I until j is less than size. This will ensure that we don't get any duplicate collision results inside of our final thing. So that's good. This should successfully find any collisions that are currently happening in the frame. Next, we update the forces, like we said. Now we want to resolve the collisions via impulse resolution. So we'll say for, and this is actually going to be via iterative impulse resolution. So the way that the impulse resolution actually works is you remember I showed you all the math and stuff, but what I didn't tell you was that actually this is all happening over an integral. Integral is just a mathematical term for calculus, which basically means that you are summing up two values or summing up some equation between two times. So like say between the last frame and this frame infinitely. So an infinite amount of time. So you sum it up basically between that whole thing, the infinite amount of time. We can't do that clearly because it would crash our computer if we tried to go to infinity and sum this equation up. But it will converge to a solution around a certain amount of iterations. So we can go and say we'll iterate a certain amount of times to get an approximate solution. And so that's why we're doing iterative impulse resolution. So we will do the impulse resolution several times, which will get us closer to the actual result, giving us a more realistic simulation. So we'll say for int k equals 0 and k is less than 6, k plus plus. This is our iterative impulse amount. So we'll just go here and say private int impulse iterations equals 6. And that's basically how many iterations we will go and resolve our impulse for, which will give us an approximate solution that looks decent. Then we'll say for int, if you want it to be more accurate, you could increase the impulse iteration, and that should give you a more accurate result. Then we'll say for I equals 0 until I is less than collisions.size. So we're looping through all the collisions now. We'll say int j size equals collisions.getI.get contact points.size. So each collision has the potential to have multiple contact points, and we need to resolve every single contact point with their impulse. Right now, we know we're only going to have one contact point because they're circles. So you can only ever have one contact point between two circles. Then we will say for int j equals 0 until j is less than j size, j plus plus, which will basically just say we're going through all the contact points that are inside of this collision that we're working on currently. And then we'll say rigid body 2D, R1 equals bodies1 dot get I rigid body 2D, R2 equals bodies2 dot get I. This will get us both of the bodies inside of that are currently colliding together, which we know is true because we add them at the same time, which means that they'll be synced up at the same position, the same index. Then we'll say apply impulse R1, R2, and then collisions dot get I. And so this is a function we do not have, but we will write now. And this is what is going to apply the impulse for us. So we'll go down here and we will just say public void. Well, actually this could be private. We'll say private void apply impulse. And this will take in a rigid body R1 and another rigid body R2. And it will take in a collision manifold, which we will call M. And let's actually call these A and B instead, just because it's a little bit easier for me to think that way instead of R1 and R2. Now, we are just going to plug in that equation that I talked about. So first, we need to solve for our linear velocity. Ideally, we would solve for angular velocity after this, but we don't really know how to do that yet, so we're going to wait on that. So say float inverse mass 1 equals A dot get inverse mass. We don't have that. Let's add that real quick. Go back into rigid body. Say public float get inverse mass, return this dot inverse mass, go back into physics system, and then we'll say float inverse mass 2 equals b dot get inverse mass, and then we'll say float inverse mass sum equals inverse mass 1 plus inverse mass 2. The reason we're doing this is because we're going to be using these a lot throughout this function, so it's better just to cache them right here. Then we'll say if the inverse mass is sum equals 0, which it should never because we're already checking for that, but just in case, we will return. This basically just means we have two infinitely massed objects, and if that is the case, then we do not want to run this equation on them because it will crash our program with a division by 0 or something. Then we'll say relative velocity. So we're going to solve for the relative velocity. We'll say vector 2f relative vel equals new vector 2f b dot get velocity dot sub a dot get velocity, which we do not have. So let's go and add that getter real quick too. Right below, nope, we don't even have a set velocity. So we'll just go over here and then we'll say public void set velocity vector 2f velocity. Then we'll just say this dot velocity, linear velocity dot set, and we'll set it to whatever they pass in. Say public void get velocity, return this dot velocity, linear velocity. So when we're talking about velocity, we're referencing the linear velocity in this case. And then we'll specify angular if we're talking about angular velocity, which we don't have to worry about right now. Okay, so relative velocity is just b's velocity minus a's velocity. And then we'll say vector 2f relative normal is just new vector 2f m dot get normal. Right, the relative normal is just that normal, and we want to make sure we normalize it as well so that it is a unit vector. So just normalize that, and now we have the relative normal. And then we will say if they're moving away from each other, we want to do nothing. And we'll say if relative vel dot dot relative normal is greater than 0, then that means they are moving away from each other. So we'll return. That's just according to the physics. And the reason we return if they're moving away from each other is because we don't want to resolve an impulse if they're already resolved itself, right? If they're already moving away from each other, we don't need to do anything because they will eventually resolve themselves. Okay. Then we'll say float e, so this is the coefficient restitution, equals math.min, a.coefficient restitution, b.coefficient restitution. Let's add those real quick as well. So go into rigid body. We will just go down here, say private float core equals, I'm going to do 1 for perfect collisions, and we'll just say coefficient of restitution. And then I'll just say alt enter and then create getter and setter. All right, go back to physics system. We'll say get core because that's what it creates it as. Okay, so now we have the coefficient restitution. We just choose the smaller of the two. It doesn't, I guess it does matter, but it'll give us a realistic result if we just choose the smaller of the two, which is fine with me. Then we'll say float numerator. So this is like the numerator of that big fraction that we had is negative 1.0f plus e times relative L dot dot relative normal. So this is the numerator in that big fraction that I was talking about. And then float j, this is the capital J equals numerator over the inverse masses sum. And then we can just say if m dot get contact points dot size is greater than 0 and j does not equal 0.0. What we want to do is we want to say j divided by equals float m dot get contact points dot size. So basically, this is the impulse for the entire rigid body. And if we have multiple contact points, we just want to make sure we distribute that impulse evenly across the contact points, which you could do it a little bit better by distributing it according to how much impulse should be applied to each contact point. But once again, this will give a realistic enough result. So we just distribute it evenly across all contact points by doing this. Then we'll say vector 2f impulse equals new vector 2f relative normal dot multiply by j. So we just turn it into a vector by multiplying the collision normal by our impulse value, and that'll give us a impulse in the direction of the collision normal. And then we'll say a dot set velocity new vector 2f a dot get velocity. So we're going to say a's velocity plus a new vector 2f, which is the impulse, times the inverse mass of a times -1. Okay, so that one's kind of big. Let's move it to a new line just so that we can see the whole thing. We're just doing that one big equation. It's actually not that big too, but it looks big because of the way we have to format it to make sure that we don't actually modify any vectors inappropriately. So then we'll do the same thing for b. Just change this to b and change this to inverse mass 2, except we're going to give him a +1. So he's added, he's subtracted. All right, and that should be good though. This should apply a linear impulse to our objects appropriately. Now we need to test this. So first of all, I'm going to modify this function and just say Boolean add gravity, which will basically just mean, do we want to add gravity to this object or not? And then if it's set, then we'll just add gravity to whatever object's being added to our physics system. And then I'm going to go into our level editor scene and we will just make some changes real quick. So I am going to comment all of this back in because I had this before and then removed it. Now we need to make sure that we say true for this one, and then I'm just going to say false for this one. And then we're going to place object 1, which is a circle at 100, 500. Then we're going to place object 2 below it, so 100 and 300. And then we will go ahead and I'm just going to do an enter here so that we can keep track of everything. So this is all good. Now we want to attach colliders to these. So we'll say circle C1 equals a new circle and hit alt enter to import that. Then I'll just say C1.setRadius to 10.0. and then I'll say C1.set rigid body to RB1. So this is just gonna be a circle with a radius of 10, and then we'll say circle C2 equals a new circle. And I'm gonna set C2's radius to 20 since it's twice as big as circle 1, and then C2.set rigid body to RB2. So that's set up appropriately. And we'll say RB1.set collider to circle 1, RB2.set collider to RB2. And this should be C2. This will be all done automatically for us. Once we get this physics system completely done, we just have to do it manually to sort of set everything up appropriately. Then we'll just go down here to my render method. You may have a different render method, that's fine. I'm gonna uncomment this and then just say add circle. And I'm going to also change this to add circle. And this basically just expects a radius here. So we'll just say 10.0f for circle 1 and then 20.0f for circle 2. And then if we hit play, fingers crossed, everything should work. I'm going to have some stuff in the way. We get a huge problem here too. Well, not huge problem, but the problem with this is we never cast these to circles. So inside of this function, just make sure you cast these to circles, because basically what ends up happening if we don't is it just recalls this function again, and then that's why we just got that infinite recursion right there. Run this again. We should be good now. Okay, there we go. And you'll notice the circle starts falling. It's kind of hard to see because I've got everything else up and running. So if you've been following along with the game engine series as well, I'm just going to comment out our scene rendering. So we should be left with debug drawing only. And then I'm also going to go ahead and comment out the grid lines so that we can just see the two objects. And then if I go back in, now we just get the two objects. And let's see if our impulse is working correctly. Fingers crossed it is. All right, cool. You'll notice that they're not slowing down too. That's because we don't have any friction applied right now, but we'll apply friction at a later date, probably next episode or something. Let me show you real quick what happens too if you mess up this. So if we don't actually subtract one of them and add the other, if we just add both of the impulses to these objects, then what we end up with is the objects start going in the same direction. And so you'll notice they just shot off down there. And then if we subtract them, you can see it a little bit better, but now they'll go up instead of down. And the reason this happens is because if you don't change the sign of what's happening from one to the other, then they basically just both take the result of the equation and apply it in the same direction. And so that's why you have to make sure that you subtract one and you add the other. That way they go off in the right direction in response to each other. And so then if we do this, once again, we will see that these circles collide in the appropriate places. If you wanted to do multiple circles, you will notice that this will work just the same. If you start getting weird errors, we will resolve those later on once we do the last step, which is applying linear projection to correct for any sort of syncing issues, which we'll talk about in greater depth in another episode. But that is it for this tutorial. It's been a long one, but we got quite a bit done, and our physics system is now finally starting to take shape. Next episode, I'm not sure, we might do friction. We might start implementing boxes to get this all done, because we can't really do angular stuff until we get boxes working with our linear impulse resolution. So we might do box collision manifolds so that we can see how this works when we have boxes in this. That is it for this tutorial, guys. If you enjoyed it, please hit like and subscribe, and I'll see you in the next one. Thanks.